Okay. Assalamu alaikum, everyone. Hello, everyone, to our sixth lecture on selected topics of radiation physics. So I want to recap of what we have discussed last time. So this is lecture 6, but probably I want to just go back and recap what we have discussed so far. I know there are a lot of equations, a lot of new things to a lot of you, but I will try to emphasize on what's really important. So we talked about there are several interactions for photons with matter. We started with Thomson scattering, and we said that this is it's an interaction of a photon with a free electron. And basically what happens is that the photon...
دكتور وميد مفيش presentation.
Okay, sorry. Yes. الحين واضحة. Can see the presentation.
Yes.
Okay. So we talked about Thomson scattering, and we said this is an interaction of a photon with a free electron. And of course, we have to understand there are no such thing as free electrons in matter. Electrons are always bound to an atom. They're always in motion. But Thomson scattering assumes that the electron is actually free and is stationary. And what happens is that the photon, when it interacts with the electron, then the photon will be scattered at an angle different than the original direction, and but it will have the same energy. And in this interaction, there is no energy transferred to the electron. Okay, so the photon is just incident on hitting the electron, and then it's scattered with the same energy, but at a different angle. And we talked about the differential cross-section. Is this concept of the differential cross-sections, is it clear to you? What does it mean? Or it's not clear? What do you mean by differential cross-section? Basically, think of the way I like to think of this is that imagine we have, this is a target, okay? And we're shooting, so the photon will go and hit anything in this target. So in this target, for example, suppose we have an area here, small area. If the photon hits this target in this area, then it's going to be scattered at a given angle. So this angle could be, for example, okay, and also a specific angle of phi. We're talking about a solid angle because now think of an electron and we have a sphere around the electron. Okay. So the photon is incident by hitting the electron, and then this photon is going to be scattered and will be incident or will come out from a certain area within that sphere. This area, this is what we call the d omega. Okay. And so the differential cross section is basically what is the area. So this thing here is actually here. So think of this area. Okay. If the photon hits one of any part of this area, it is going to be scattered at a given solid angle. So the differential cross section is basically what is this d sigma, such that the photon is going to be scattered at this d omega, this solid angle. To get the total cross section, all what we need to do is just add up, because each area, if the photon is incident on different areas, it will be scattered at a different angle and different d omega. So if we want to calculate what's the total cross section means that the photon is going to interact. We don't care where it's going to go. So all what we need to do is just sum up all of these areas. So this is in notation. This is when so here, for example, this is the differential cross section. And then this with respect to theta. And then when we integrate, we get this area here. So this is basically the area. Think of this as a virtual area in front of the electron. If the photon hits that area, then it's going to it will undergo Thomson scattering. And in this case, for Thomson scattering, the total electronic cross section is independent of the photon energy. So it doesn't matter what photon energy is, and it's constant. It's 0.665 bars. But although this
دكتور محمد عندي سؤال.
Yes, اتفضل.
أنا مرات عشان أفهم شوية الكروس سكشن بحاول أفهمها وكأنها probability.
Cross section is not a probability. Cross section is
But
something we can calculate from it probability. I will give an example. For example, if I ask you what, so suppose we have this figure here, we have this thing here, and I ask you, okay, what is the probability that the photon is going to be scattered at a specific angle, theta and phi, whatever that angle is, it's going to be scattered at that angle. All what you need to do is, okay, look at the area, the differential cross section, where, okay, if the photon hits this area, it's going to be scattered at this, going to be in this direction, and we divide by the total cross section. That will give me the probability. So the probability, for example, of the photon being scattered at this location or this solid angle is going to be equal to this differential cross section divided by the total cross section. So we use the cross section. Remember, it has a unit. Okay, its unit is area, right? Or it's bars. So it's an area. An area is not a probability, but we can use the differential cross sections to calculate probabilities. Okay, so it's not directly a probability, but it's somehow related to probability. So if the differential cross section is high, that means, oh, okay, the probability is high, but it does not equal to the probability. That's what I want you to distinguish.
Okay.
Okay.
Yes.
So, and then we move to Rayleigh scattering. So Thomson is I don't know if it happens I mean, I have really some doubts that it actually happens. Many people say, yes, it happens at very low energies. My problem is, okay, if you look at the total cross section for Thomson, it's actually greater than for Compton. But so in megavoltage, we see Compton scattering, we don't see Thomson scattering. So anyway, that's so the way I like to visualize it is like a theoretical concept of interactions, but we use it to describe other interactions. So from Thomson, we went to Rayleigh. And Rayleigh, what is different than Thomson is that it's an interaction of a photon with an atom. It's not an interaction of a photon with an individual electron. Again, what happens is that the photon is scattered with the same energy, but is scattered at a different angle. And also there is no energy transfer to electrons. So the electrons or, the atom will vibrate or okay, deflect the photon, but no energy is given to any of the orbital electrons. Okay. This is important, an important concept that we have to understand. Later on, when we want to calculate doses, the first question is, okay, what's the energy actually transferred to a charged particle? That's the main thing. And I showed you some of the figures on how the differential atomic cross-section for Rayleigh. And the basic idea is that for Rayleigh, the differential cross-section and also the cross-sections, they are actually proportional to Z squared. Okay, because it's an interaction. Remember, it's an interaction with an atom. So if we compare, for example, the total cross-section for Rayleigh for let's say carbon compared to hydrogen. So for Rayleigh, it's going to be 36 times more because it's proportional to Z squared. For carbon, Z is 6, hydrogen Z is 1. So therefore, Rayleigh cross-sections are 36 times higher or larger than hydrogen. So this is some physics, how this the differential cross-section. Also another thing for Rayleigh scattering is as the photon energy increases, the scattered photon is more in the forward direction. So when we say the probability is, now we're talking about areas of these cross-sections. So we can see here in the figure that at least, this here, the peaks, the areas under here compared to the full curve. So this is the full curve. Okay, so this is the full curve. And if we're looking at the photon being scattered, let's say between 0 and let's say 45 degrees, the area here is very large when we compare it to the full differential cross-section. This means that we have a higher probability of the photon being scattered more in the forward direction. One thing also with respect to energy, the cross-sections for Rayleigh scattering, they decrease with photon energy. And it turns out that they are decreased as 1 over h mu squared. So for Thomson, it's energy independent, it's constant for all photon energies, whereas for Rayleigh, it's actually decreases with increasing photon energy. Okay, so this is here in the box, highlighting the box. The atomic cross-section is proportional to Z squared, and the atomic cross-section for Rayleigh is proportional or inversely proportional to the energy of the photon squared. What does this mean? It means that if, for example, if we know the cross-section of Rayleigh, let's say at 10 keV, what will happen to the cross-section if we doubled the photon energy? So now it's 20 keV. We would expect that the cross-section, the atomic cross-section for Rayleigh to be 1 over 4 of that when it's 10 keV. Okay. And then we move to the important interaction, Compton scattering. And we said that Compton scattering is an interaction of a photon with a free electron. At least based on this concept, we could actually calculate a lot of the useful stuff for Compton. What's different between Compton scattering and Rayleigh or Thomson is that in this case, the photon is going to be scattered with a lower energy. And this means that some of that energy is going to be given to the electron. This is the energy transfer. Okay? So the transferred energy to the electron is given by the energy of the incident photon minus the energy of the scattered photon. We can use conservations of energy. These are the equations for conservation of energy. We look at the energy before the interaction and after the interaction, and it has to be conserved. And also, we look at the conservation of momentum and the x-axis and y-axis. Momentum should also be conserved. So before the interaction, for example, momentum, we only have momentum from the photon. The electron is at rest, so it does not have momentum. And after the interaction, we have a momentum. A photon now will be scattered with a lower energy, so it has a momentum, and the electron will gain some energy, so it will have a momentum. So using these equations for conservation of energy and momentum, we come up with these important equations. One of them is, for example, the Compton wavelength shift equation. This is basically relates what's the wavelength of the scattered photon compared to the incident photon, or the shift in the wavelength. It's given by this equation, where lambda c, this is what's called the Compton wavelength of an electron. It's a constant, and it equals to 0.0244 angstrom. The energy scattered fraction, this is important. Okay? We want to know, okay, how much of the photon energy is lost. So it's basically, or the ratio. This is basically the ratio of the energy of the scattered photon to the energy of the incident photon. It's given by this equation, where this epsilon is given by h mu over MEC squared. And the energy transferred fraction, this is how much energy fraction, it's a ratio, okay, that the electron is going to take. So we can, it's just 1 minus this, and it's basically this equation. I always memorize this by the denominator. It's 1 plus epsilon 1 minus cosine theta. So for scattered photon, we will put the 1 here. And for the scattered, for the electron, if you're interested in the energy of electron, we'll put this part, we'll put it here. Notice that the energy of the scattered photon, or the energy of the transfer to the electron, will depend on two things. Will depend on the energy of the incident photon, as well as on the scattering angle. So to calculate, in order to calculate how much energy is transferred to an electron, if the photon undergoes a Compton scattering, we will need to know what's the energy of the photon, as well as what's the scattering angle of that photon. If we know these two things, we can immediately calculate what is the energy of the scattered photon, as well as what is the energy, this is the scattered photon, what's the energy of the recoiled electron or ejected electron. We talked about this nice concept is, okay, suppose now we want to look at, let's say at 90 degrees. Okay, so all what we're going to do here, we want to see what's the energy of the scattered photon when the scattering angle is 90. So cosine theta, 90, this is 0. So the point is, we want to see what's the maximum possible energy of the scattered photon at 90 degrees. So we start to crunching the numbers, put the photon, incident photon of 1 MeV, 2 MeV, 3 MeV, 100 MeV, 1,000 MeVs, and so on. And this is the curve we're going to get. So for scattering at 90 degrees, the curve will look like this. So it saturates, or it actually goes to a specific value. And that value is 0.511, or MEC squared. We can generalize this concept by just using this equation and getting the limit as the energy goes to infinity. So this is the maximum of the saturation energy of the scattered photon. It's given by this formula here. So for when theta equals to 90, this cosine is 0. So it's just going to be equal to 0.511. Now, for a backscattered photon, if the photon is scattered in the backward direction, the scattering angle is 180. So we're going to put cosine theta. We use 180 degrees. So cosine 180 is -1. 1 minus -1 is 2. And this is how we arrive that, okay, when theta equals to pi, the maximum possible energy, regardless of the incident photon energy, it's going to be, it has to be less than MEC squared over 2, which is 0.255. These are useful concepts, especially when you want to think of shielding and looking into, what's the energy of the photons, incident on a specific barrier or to calculate what's the maximum energy transfer to an electron when a quantum interaction happens. The maximum energy transfer to an electron will always happen when the photon is backscattered. But otherwise, if we look at this equation, when is this equation maximum? This equation is going to be maximum when theta equals to 180 degrees. That will be the maximum possible energy that the photon can transfer to the electron. So it's given by this formula here. And we can, for example, at 1 MeV, if the incident photon is 1 MeV, the value of a transfer to the electron when the photon is backscattered is going to be 0.8. Okay, and if the photon energy is, let's say, 100 MeV, it's almost going to be 100 MeV. Okay, so what we see is that as the photon energy increases, actually, more of the photon energy will be given to the electron. So look at a photon of 100 keV, only 0.25 or 0.3 of its energy will be given to the electron. If the photon is 1 MeV, 0.8 or 80% of its energy will be given to the electron when it's undergoing backscattering. Again, this is the differential cross-section for Compton. It's based on the Thomson with the F-Klein machine. I will not go in details into this. But again, the important thing is we see that actually as the energy of the photon increases, the area under these curves will decrease. So we would expect that Compton, for the total cross-section for Compton, as the photon energy increases, this the total cross-section is going to decrease with energy. Okay, this is a plot of the Compton cross-section for different atoms, lead, copper, and so on. And again, as I mentioned, that as the photon energy decreases, okay, the Compton cross-section decrease. As the photon energy increases, the Compton cross-section decreases. Now, with respect to Z, for example, remember we said the Compton scattering is an interaction of a photon with an electron. Okay, so we have a total cross-section for an electron. Now, if I have an atom, let's say carbon, what is the total cross-section for carbon then? Carbon has 6 electrons. So all what we do is we multiply the number of electrons by the Compton cross-section per electron. And this tells us that Compton scattering, the cross-section is proportional to Z. Really, it was Z squared. In Compton, the atomic cross-section is proportional to Z. So hydrogen, carbon, 6 times more. Aluminum is going to be 13 times more. This is in a log scale. Okay, don't let the scale deceive you. This is a log scale. Lead is going to be 82 times more than hydrogen, the atomic, because lead has 82 electrons. Now, one thing we've also discussed is, okay, this is the theoretical. If the electron is free, that's not a problem. But in reality, electrons are bound. So as the photon energy decreases, we find actually the Compton cross-section actually will decrease, because now the lower the photon energy is, okay, the less number of electrons can interact because they're bound. We need to give them energy so that they can overcome their binding energies. So this explains why at low energies, the Compton cross-section actually decreases. This is the dotted line. This is the theoretical, or what's based on the Klein-Shina model. Electrons are free and stationary. In reality, electrons are bound. So at low energies, yes, the theoretical curves are not correct. We need to take the binding of the electrons into consideration. However, if we go to higher energies in the megavoltage and so on, we don't see a difference between the theoretical and the actual cross sections, because the binding energy of the electrons are negligible compared to the energy that is going to be transferred to them from the interaction itself. Now, this is an important graph. Because now later on we want to calculate the doses, so we need to know what is the energy transfer to an electron. But the problem we face with Compton is that depending on the scattering angle, the energy of the electron is going to be different. So what we can do, we can then average things. We can take, okay, what's the mean? We have to look at, okay, suppose I have a 1 MeV photon. What is the energy of the electron if the scattering angle is 10 degrees? What is it? Is 20 degrees, 30 degrees, 40 degrees. So we need to know, for example, we can calculate what's the energies given to electron at these specific degrees up to 180, but we also need to take into consideration what's the probability of the photon being scattered at 10 degrees and 20 degrees. They're not equally probable. And this is where, Hussein, this is where the cross-section, the differential cross-sections have a role there. So the equation or the way to calculate what's the mean energy transfer fraction is, now we need to do this integration where we're using the differential cross sections, and then here we have to multiply it by the energy transfer, and here we don't. So the ratio will give me the F, and it's a very horrible equation. If you look at the book, it's like 3 lines of luckily for us, if we plot this curve, okay, we will get this sigmoidal curve here. So at 1 MeV, for example, these are anchor points. 1 MeV, the average energy transfer to electrons is going to be 0.44. Some electrons will have higher energies depending on the scattering, if the scattering angle is large, or vice versa. But on average, when we're here, we're talking about on average, we're not describing one single interaction. We're describing millions and millions of interactions. Because since all angles are possible, we need to get the probability of the scattering within a specific angle, and we multiply by the energy of the electron when that interaction happens. And then we need to average this out. This will give us this graph. And again, what we see is that the higher the photon energy is, the more energy is actually, or the average energy transfer is actually increases. Okay? So these are anchor points. At 100, it's 0.8. At 1, it's 0.44, and so on. This is in comparison to this curve here. This is the maximum. This is when we have the theta equals to 180 degrees. But this curve is the average. Okay? I hope you distinguish between the two. So the average for 1 MeV is actually 0.44, whereas the maximum energy transfer is actually 0.8. Here, this final graph for Compton scattering, this just shows you Rayleigh, because both are scattering interactions. So Rayleigh, this is the cross-section for Rayleigh, and this here is the cross-section for Compton scattering. So at low energies, we see that the cross-sections for Rayleigh are higher than that for Compton. And what we also see that they depend on Z squared. Whereas for Compton, see this is lead compared to hydrogen. Look at lead compared to hydrogen. This is a log scale. Look how many cycles it's there. But here is a little bit less. So for Compton, the atomic cross-section depends on Z. And it decreases with energy. okay, when binding effects are negligible. We're not talking about this region here. We're generally more interested in this region at high energies. So in general, the Compton cross-section decreases with photon energy. Okay. So now we come to another interaction, which is the photoelectric effect. Photoelectric effect is an interaction of a photon with an atom. In some books, you will find that, okay, it's an interaction of a photon with a tightly bound electrons, okay, which is correct. It's just, I want you to now I want to discuss something so that we understand these concepts more. So with an atom, when I say it's with an atom, it's basically with electrons that are bound to an atom. What happens is that the photon is absorbed completely. We don't have a scattering from photon. And that energy of the photon is then given. It's taken by the atom and it's given by the atom to one of its orbital electrons. Usually, it will give it to the tightly bound electrons. The more closer or more tightly bound, as long as that energy is sufficient for the electron to take it and be ejected, the atom will give that energy to that electron. For example, lead, the binding energy, the K shell, is 88 keV. So if a photon of 100 keV interacts with lead, the photon will disappear. This 100 keV will most likely be given to a K shell electron. And the K shell electron will be ejected with an energy equals to 100 minus 88, which is 12 keV. That's the kinetic energy of the ejected electron. However, if the photon is actually has, let's say its energy is 80 keV, the atom cannot give the 80 keV to a K shell electron. So it has to resort to, okay, the next level. So probably it's going to give this energy to an L shell electron. Okay. So it will always, it's possible, by the way, it is possible that even if the energy is 100 keV, the energy goes to an L or an M shell electron, not necessarily to the K, but the probability for the K is much higher. It's about 80 or 90%, depending on the Z. So I have a question. Can we have something, can a photon? So imagine we have an electron stationary. And this is the photon, has an energy h mu. This is before the interaction. And can the photon give all of its energy to a stationary electron or not? Is that possible or not? So we have this is the electron, and now the electron is going to come out with a kinetic energy. Okay. Remember, in Compton, the photon gives part of its energy to the electron, a free electron. Okay. My question, can the photon give all of its energy to the electron or not? So in order to answer that question, anyone knows the answer? يعني بالعربي عندي في الكومبتون قلنا الفوتون لما ينتراكس بدي جزء من طاقته للالكترون، والفوتون سكاتر اتشتت بطاقه اقل، والطاقه اللي هياخدها الالكترون هي الفرق بين طاقه الالكترون طاقه الفوتون الساقط الانسيدنت وطاقه الفوتون المشتت. الان سؤالي انه هل من الممكن انه الفوتون يدي كل طاقته للالكترون ولا ما ممكن؟ So in order to see if such an interaction is possible or not, we look at conservation of energy and momentum, and we see, is that possible or not possible? So let's look at before the interaction. Okay. So let's look at here. So what's the total energy of the system? We have h mu, it's the energy of the photon, plus MEC squared. That's the energy before the interaction. What's the energy, the total energy after the interaction? Of course, there is no photon. We will get this kinetic energy of the electron. Okay? So this is the first equation. We will write it here. H mu plus MEC squared equals to, and here, of course, we have also the electron. So we have the rest mass energy of the electron plus the kinetic energy of the electron. So H mu MEC squared equals to kinetic energy plus MEC squared. Okay, this will go.
بس مش احنا افترضنا دكتور
تفضل.
والجهة الثانية على اليمين مش احنا مفترضين انه الالكترون هو ستيشنري، كيف بده يكون في عنده MEC سكوير؟
لا الحين صار الانتراكشن. قبل
اوكي
الانتراكشن الالكترون
تمام
ستيشنري. الحين صار الانتراكشن، الفوتون
اوكي
اعطى كل الطاقه بتاعت الالكترون، فالالكترون صار عنده kinetic energy. مظبوط؟
اوكي
اوكي؟ طيب فالحين from here what do we get? We get H mu equals to EK. طاقة الإلكترون هتساوي طاقة الفوتون الثاني. تمام؟ Now let's look at momentum. So the momentum before the interaction, the electron is stationary, so it does not have momentum. So we have momentum of the photon. And after the interaction, we don't have a photon, we have an electron. So we have a momentum for the electron. So based on this, we will get the photon momentum or the electron momentum has to equal to a photon here. Now, let's do something more. So the photon, the momentum of the photon is h over lambda. It's HC over lambda, sorry, it's HC over, yes. Okay, or we can write it, I like to write it this way, sorry. Okay. So it's HC over mu. It's mu over C, sorry. It's H mu over, I get confused. So H mu over C. Okay, remember, it's H over lambda, and lambda is C over mu. So then we get H mu over C. This equals to the momentum of the electron. Momentum of the electron is basically equal to, I don't know if you know this equation or not. We get it from here. This is the total energy, this relativistic, equals to the rest mass energy squared plus the momentum C squared. So for an electron, we need to get the momentum of the electron here. So this will be the total energy, which is the kinetic energy, E kinetic, plus MEC squared, all squared. So it's this part equals to MEC squared, all squared, plus EC all squared. Okay. So from here, we can do a small trick. We can just do this PD. Okay, and you put C, and we remove this C from here. Okay, because we want this PC. So what we get H mu equals to, and it's going to equal to the square root of the kinetic energy plus MEC squared all squared minus MEC squared all squared. Okay. We can make things a little bit nicer. So here we can take, this is EK squared plus 2, it's MEC squared, EK minus MEC squared all squared, and here there is a plus MEC squared all squared. So this فكيت هذا التربيع. But this will go with this. And what we get at the end, we get HU equals to EK plus 2ME C squared plus HU plus EK. Now, this equation tells us that EK equals to HU. That's from conservation of energy. So if we put this back, we put it here, we get HU equals to, we can put here HU, and then we have here HU plus 2mc squared. Okay. Now, when is this? How can this energy, photon energy, equals to this some there plus a value there? This can never be zero unless HU equals to zero. The solution to this equation is HU equals to zero, but the energy of the photon is not zero. So this tells us that actually this interaction cannot happen. We cannot have a free electron and a photon giving all of its energy to the electron. It can never happen. Because we cannot have conservation of energy and conservation of energy in this case. This is why for photoelectric effect, we will need an atom. The electron has to be bound. When we have a free particle, yes, this probably we can have actually this interaction because the atom is going to take some of that energy. Anyway, I just wanted to show you that photoelectric effect is an interaction of when we say it's with an atom, we need to have the electron bound. The electron can never be free. Otherwise, this interaction can never happen. So now the photoelectron happened and the electron is ejected. Now, what's the angle of the electron going to be? This is not really of a lot of, it's not really important, but just to give you an idea, is that the electron, the distribution of the electron. So if, for example, we have a 10 keV, let's do this. So this curve is for the 10 keV distribution. So if the photon energy is 10 keV, okay, we will find electrons being ejected at 20 degrees, 30 degrees, and so on. They will form this distribution. So it's very likely the mean or the most probable angle of the electron will be very close. It's actually going to be very close to 90 degrees. Yeah. Okay. As the photon energy increases, the electron, when it's ejected, it's more ejected in the forward direction. So think of this figure here. This is the incident photon and this is the atom. We're talking about the angle of the electron when it's ejected. If the photon energy, as the photon energy increases, okay, we would expect this ejection angle to be more in the forward direction, means to be closer and closer to zero. Okay? We can have an electron even ejected at 180 degrees. That's possible. But the probability is very, very, very low. So this the angular distribution of photoelectrons depends on the incident photon energy. For low energies, the mean ejection angle is very close to 90 degrees, as shown here. Okay, this is the mean, the average, or the peak. As the photon energy increases, this mean of the ejection angle actually tends to be more in the forward direction. Here, this is a 10 MeV. We have a photon 10 MeV, and look at the distribution or the probability of the angle for the ejected electron. We see it's very, very close to zero. So it's more in the forward direction. It's really not an important concept because the electrons, as we will learn later on, the electrons, as they're ejected, they will be scattered, a lot in the medium. So it's not really, it's not like photons when they're scattered. The electrons, they will interact with the next atom and so on. So they will be deflected a lot in the medium. Now, this is an important thing. Now, this is the atomic cross section. for photoelectric effect. We find something unique to photoelectric effect for the atomic cross-section. We find that actually it exhibits like some sawtooth structure or a discontinuity. And these discontinuities happen at the K edges or the L edges or the binding shell energies. So here, this curve is for lead. We see that, okay, the cross-section before the photon energy reaches 88 keV, this is the curve, it goes down. But suddenly, when the photon energy increases, becomes higher than 88 keV, we see that the cross-section suddenly, has a discontinuity. It increases by an order of magnitude. This is not a small increase. This is a log scale. It's an order of magnitude, which tells us actually photo effect loves, these tightly bound electrons. Imagine for lead has 82 electrons. We have only 2 electrons in the K shell. So if the photon is just less than 88 keV, this photon can interact with 80 electrons because the binding energy of these 80 electrons is low. The photon can interact with them. So the atom can give the energy of the photon to 80 electrons. But now imagine if we just increase a little bit the photon energy, so that's just above 88 keV. What happens? We added only 2 electrons, possibility of interactions. But what happens to the cross-section? The cross-section increases by an order of magnitude. So this tells us, okay, no, it's actually the cross-section, photo effect loves actually to give the tightly bound electrons its energy. So this is why in the definition sometimes you find in photo effect, it's an interaction of a photon with a tightly bound electron. It's because this is what we see in the cross-sections when we plot the cross-section as a function of energy. We see these discontinuities, and it's the cross-sections increases, by an order of magnitude. For copper, this will happen at about 9 keV because that's the binding energy for K shell electrons. We see again this discontinuity. And you can imagine we're also going to see discontinuities at the L shell, and probably we're going to see 3 edges there. Remember, the L shell has 3 energy levels, and on the M, probably we're going to see 5 energy levels there. Okay, so this is something unique to photoelectric effect. We don't see these discontinuities in Compton or in Rayleigh cross-sections. Now, this equation is basically what's the atomic cross-section. I don't want you to, this is not really important. The important thing is we want to see what's the dependence on Z. Okay, so this equation is basically the atomic attenuation coefficient or atomic cross-section for the K shell electrons. Now, one can argue, okay, what happens to the L shell and so on? Okay, these are irrelevant because the most of the cross-section is actually coming from the K shell electrons. So for K shell electrons, we're describing the cross-section beyond actually the K edge. It's given by this formula. Again, we see our nice Thomson electronic cross-section. This is here the energy dependence. Epsilon is the energy divided by MEC squared. But with respect to the atomic number Z, it's Z to the power N. And this N is for low energies, it's about 4, but the N could actually be around 4.6 for higher photon energies. But usually the standard we say, okay, for the atomic cross-section is proportional to Z to the power 4. We usually say Z to the power 4 dependent. Okay. And this is here the cross-section when we're talking about very high energies, more in the relativistic case. Actually see the dependence on Z goes to power 5. But for most part, for our medical physics applications, we always state that, okay, the atomic cross-section for photo effect depends on Z to the power 4. With respect to energy, we see that, okay, with respect, except at these discontinuities, we see, for example, that the dependence is 1 over h mu to the power 3. So it decreases with energy near the k edges. This decrease is 1 over, it's a rapid decrease with respect to energy. But as we go far away from the k edge, the decrease with respect to energy, it goes actually 1 over h mu. Okay. And usually for diagnostic applications and so on, we are dealing with in this range here. So this is why you'll see in a lot of books that the photo effect, the atomic cross section depends on z to the power 4 and inversely proportional to the energy to the power 3. Now, this is a very important concept. Probably, I'm not sure if you have taken this or not, but I would like you to explain it because it's a nice concept. So now what we want, again, like for every interaction, we need to calculate what is the energy transfer to electrons. That's very important for us in physiology. For Rayleigh, we said no energy transfer to the electrons. For Compton, we are going to use the graph, that sigmoidal shape. That tells us what's the energy or the mean energy transfer to electrons. How about for photoelectric wave? Well, we have our atom and we have our electrons. So here, these are the patient. So now the photon, when it interacts, we have a photon, interacts. What is going to happen? This electron is going to be ejected. We're going to end up with a vagus. So the energy of this electron, this is called a photo electron. The energy of this is h mu minus the binding energy, and we'll assume it's coming out from the patient. So h mu is the energy of the photon, h mu minus the binding energy of this electron. But now with photoelectric, a vacancy is created. So when we have a vacancy, we're going to have transitions. Just give me a minute, please. Sorry for that. Okay, so we're going to have a vacancy, and whenever we have a vacancy, we know what's going to happen. We're going to have relaxation. And with this relaxation, we're going to either get characteristic photons or we can get Auger electrons, right? So when we want to calculate the energy transfer to electrons, we need to take this plus these Auger electrons. Because the Auger electrons will come out with energy. So how to do this? We will look at two limits. Okay, what's the limit? First limit. The first limit is that, okay, the first limit is that the mean energy transfer is limited. Okay, we will want to assume first is that, okay, after we have the vacancy, all what we're going to get from there is just characteristic X-rays. So no Auger electrons. So this means that this is the lower limit when we have full emission of characteristics. In reality, we will have some Auger electrons coming down. So the energy transfer is basically it's this quantity plus whatever energy is coming out from Auger electrons. And what would be the maximum is that if all energy, all of we don't get characteristic X-rays, all what we're getting from the atom is basically Auger electrons. So this will be limited by the energy of the photon. So the energy transfer is somewhat in between these two limits. Because whenever this happens, we're going to get characteristic photons and we're going to get Auger electrons. So if we're getting if all what we're getting is characteristic photons, this will be the energy transfer. If we're getting Auger electrons, no characteristic X-rays, this is actually going to be the energy transfer. But in reality, it's linear. So how do we do this? We say, okay, let's ignore all other shells. Let's focus only on the K shell. So the first thing we need to answer is, what is the probability that when we have the photo effect, the electron is ejected from the K shell? This is what we call PK. This is the probability that photo effect, when it happens, the vacancy that's going to be created is going to be in the K shell. The next question is, okay, what's the probability of emission of X-rays? We know that this is the fluorescence yield. Yeah, we discussed this in the earlier lectures. The last thing is, okay, what is then the average energy of these characteristic X-rays? This is what we want to call, it's basically the mean energy of the characteristic X-rays. So this is the concept, then the energy transfer equals to the photon energy minus PK, omega K, and then this thing. This gives me actually the energy transfer for photo effect. And this is not the complete picture, because someone would say, okay, photo effect, we can give the energy, we can have the vacancy in the L shell. We say, okay, no problem. Then we need to do this also for the L shell and M shell. But we usually ignore these shells because the energies of the Auger electrons for the characteristic are very low compared to the K shell. That's why I usually ignore it. So this is a good approximation that we can do. Now, PK could be calculated actually from the cross sections, but I like always using curves. So PK looks like this. Here, this is PK. We call PK, and here we have Z. So PK will look like this. Something like this. Here, probably I think around 0.9 or maybe 0.35. Z here is 1. Okay, and Z here is 150. Okay, what does this mean? It means, look, if I have a low Z material, actually the probability that the vacancy in the K shell is very high. It's almost 1. Why? Because actually, we don't have a lot of electrons. The hydrogen, for example, what's the PK for hydrogen? What effect is going to be 1, because we have only 1 electron in the K shell. Helium is the same thing. Okay, as we go higher in Z, then the probability decreases a little bit. It's still high that this will happen in the K shell, but it's not going to be 1, it's going to be less than that. So this is for the first factor. Omega K, that's the fluorescence yield. We looked at the curve. So the curve starts somewhere from 10 and around 30. The value is 0.5, and this goes like this. So this is the omega K. This is PK. So these two factors, we can get them from this step. The last one is this mean energy of characteristic photons. This is difficult actually to calculate. We need to know, for example, when I have a K shell vacancy, okay, what's the probability that the electron is going to have to fill this vacancy from the L shell or from the L2, L3? And what's going to, we need to look at, okay, these are what we call the intensity lines, and from the M shells and so on. It's very difficult to calculate. It's doable, but there is a very good approximation to this value. This, I would take it usually around 0.85 of the K binding energy. So for example, we have the binding energy for the K shell, this is 88 keV. Then we say, okay, the photon of the average energy of the characteristic photons is roughly going to be 0.85 multiplied by 88 keV. So once we have this data, then we can calculate what is the energy transfer time. The concept I want you to understand is there is going to be a vacancy, and when we are dealing with energy transfer, we are not looking only at the photoelectron. We are looking at the energy of the photoelectron as well as OJ electrons at that kind of data. One could ask, well, in Compton, we can get a vacancy. Why aren't we doing this, calculation when we dealing energy transfer for Compton? That is true. But now for Compton, we're talking about something in the megavoltage range. So usually the energies of the OJ electrons are in the kilovoltage range. They are negligible compared to the energy that is transferred to the Compton electron. So it's a good approximation to say, okay, for Compton, the energy of the transfer electron, energy transfer to electrons, we can approximate it as it's just simply the energy of the Compton electron. In photoelectric effect, because this interaction is dominant at lower energies, then to have a better estimate of the energy transfer, probably we cannot ignore the OJ electrons. Probably want to do better. Then okay, let's add these electrons. So what we're doing here is basically we're saying the upper limit is this. Okay, and we are subtracting all of the energies of characteristic photons. And this gives me the energy transfer. This is basically the energy transfer to the photoelectron plus energies that are transferred to the OJ electrons. So the energy transfer fraction is basically how much fraction of the photon energy is going to be given to the charged particle is given by this formula. It's basically this equation here. So let's remove this. So the energy transfer fraction over h cube. This is F. This is the energy transfer fraction. This is for photon effect. Is basically energy transfer divided by h nu equals to, we have this h nu minus pk omega k and h nu k divided by h nu. Okay, and this equals to 1 minus this pk omega k h nu k over h nu. This is the photon energy, the energy of the photon, whereas this is the mean energy of characteristic X-rays. Okay. So if the energy of characteristic X-rays is low, it's zero, it's almost zero, then we get, okay, all the energy is transferred to OJ electrons plus the photoelectron. These are the curves. This is, I think, this is the fluorescence yield. This is the PK. I think it's here, and so on. So we have curves actually how to do this calculation. And for the binding energy, remember, we talked about this equation and estimation. We said, okay, the binding energy. This we can estimate it as 13.6. Remember this, kV multiplied by Z minus 2 all squared. This is for high Z material. Sorry, this electron volts. It's not kV. Yeah. But usually I actually memorize the binding energy. So I know for lead it's 88, tungsten it's 70. Uranium has the highest binding energy K shell, it's 115. So if you know a few of these elements, then you can construct a curve like this, and then you can estimate for any other element just using the curve. Here we're looking at estimation of things. We're not want to do an exact calculation. Otherwise, we can just go to and open any data book and get the exact values directly from there. And this is the plot of the energy transfer fraction. If we plot it, we see as at high energies, okay, this thing here becomes negligible compared to the photon energy. So this approach is zero. That's why for high energies, it's safe to say, for example, if I have 1 MeV photon, it is safe to say, okay, probably the energy transfer, I will just take the photoelectron energy transfer to the photoelectron. That's good. Or we just say it's equal to 1 MeV. It's the same energy. But the problem is when we are dealing with an energy that is close, for example, to the binding energy. For lead, for example, if I have 1 keV, 100 keV, you see the energy transfer is not actually equal to the energy of the photoelectron, but less than that. So now pair production. Actually, pair production, there are two types of pair production. There is a nuclear pair production. Basically, in a nuclear pair production, it's an interaction of a photon with the coulomb field of the nucleus. So we have the nucleus here, the photon is incident, okay, and there is an interaction going to happen. And after the interaction, the photon will disappear, and the photon, it will create actually an electron and positron pair. And that is basically nuclear pair production. Again, a question, can a photon, for example, can a photon with energy h mu suddenly disappears and it gives us an electron positron pair? Is this possible or not? You will find if you apply the laws of conservation of energy and momentum, you will find this interaction cannot happen. Like the photo effect. Photo effect, a photon interacting with the electron and giving it all of its energy, that cannot happen. The electron has to be bound to an atom. The same thing with pair production. This interaction cannot happen, that a photon in free space disappearing and creating an electron positron pair. This cannot happen. This interaction has a threshold energy given by this formula. I don't know if you know how to calculate threshold energies for any interaction, but in our case, so for example, you have this is particle A, and then we have particle B. This is coming with a certain energy. And then what we get here, for example, another particle C and another particle D with some energies. Okay? So they each will have kinetic energies. So the question is, so this is a nuclear reaction. We have a particle hitting another particle, and we get 2 particles or 3 particles, something before and something after. So the question is, what is actually the threshold energy? Okay, what's the minimum energy that this projectile B should have in order for this interaction to occur? I won't go into the derivation of it, but if you're interested, maybe next time I can show you how what's the general formula for that. So if we apply this method to get the threshold energy, we will find that the threshold energy for nuclear pair is given by this formula here. It's 2mEc squared, 1 plus mass of the electron divided by the mass of the nucleus. You all know that, okay, it's greater than 1.022. This is true. true in the sense it's yes, a good approximation, because usually the nucleus, even if we take the lightest nucleus, which is hydrogen, we know that the mass of a proton is about 2,000 times the mass of a proton. So this fraction then becomes very, very small, very close to zero. And we get the threshold energy equals to 1.022. But in reality, it is not exactly 1.0022. It's actually a little bit high. And there is a reason why I'm putting this formula, and you will understand it now. Okay, but the point is that this interaction, unlike photo effect, Compton, or Rayleigh, this has a threshold. Threshold meaning that this is a minimum energy for the photon in order for the interaction to happen to occur. And it's given by this. Now, this interaction happened. What is the energy transfer fraction to charged particles? Right. It's the photon energy. We take from it 2 MEc² to create the electron-positron pair. And the remaining energy, this is going to be shared by the two charged particles, the positron and the electron. So the energy transfer is just going to equal, or the energy transfer fraction is going to be 1 minus 2 MEc² divided by h mu. So this is the nuclear pair production, about nuclear pair production. This interaction can also happen in the vicinity of a Coulomb field of an electron. This is now with the nucleus. And that is what we call electronic pair production. The same thing could happen. Like nuclear pair production, we can have the same thing with an electron. A photon coming in very close proximity to the electron and interacting with the Coulomb field of this electron. And what will happen? The photon is going to disappear, and we're going to get an electron-positron pair. Now, the remaining energy from this interaction actually is going to, some of it will be taken by this electron, the orbital electron. And the orbital electron is going to come out from the atom, and we're going to be left with a vacancy. So what we're going to end up with is actually three particles. Three particles, an electron-positron pair, plus the electron, the orbital electron that the photon interacted with. This is why it's called, sometimes it's called triplet production, because we get three particles coming out from the interaction. Now, the interaction has a threshold, and the threshold is given by 4 MEc². So if we go back and look at this formula here, now, instead of the interaction happening with the nucleus, now it is happening with an electron. So this capital A, this thing, now it's an electron. So we have mass of electron divided by mass of electron, which is 1. 1 plus 1 equals to 2. And we get the threshold energy for triplet production is then given by 4 MEc². However, the energy transfer is still going to be given by the same formula. This is the remaining energy of the photon. The only difference is that this energy, the remaining energy, actually this should be triplet or electronic. It should, then in this case, is going to be shared by the three particles, the electron-positron pair, plus the orbital electron that was ejected from this interaction. So here, the kinetic energy is shared by three particles, whereas in nuclear pair, we only get these two charged particles, electron and positron pair. So in general, pair production has a threshold energy. Below that threshold energy, these interactions cannot happen. For pair, it is roughly 1.022 or 2 MEc². For triplet, it is exactly 4 MEc². So the cross sections, the atomic cross sections below these threshold energies are 0. So we only see cross sections, okay, when the photon energy is above the threshold energies. If we compare the cross section for nuclear pair and for electronic pair, we find that actually nuclear pair dominates. If you look at the cross, so if, for example, I take lead and we get the nuclear pair production for lead, and then take the electronic cross section, lead has 82 electrons. So if you multiply 82, if we get the electronic cross section for triplet production and multiplied by 82, still we're going to find that the nuclear pair production, the cross section is higher than the electronic one. And this is why usually in textbooks, usually triplet production is ignored. And in some cases, it's not even taught to physicists. But it's an interaction that can happen. So here, this is nuclear pair for lead compared to electronic pair for lead. It's about an order of magnitude higher or more. It's really large. And here we have carbon and carbon. And then it's like an order of 10 times more than nuclear pair. That's why we tend to ignore the triplet production and so on. So in general, pair production, it increases with photon energy. That's one thing that we need to understand. It increases with all the other interactions, they decrease with energy. Some would decrease with proportional to the energy to the power 3. Some are Rayleigh's energy to the power 2. Compton, we don't have really a direct relationship, but we know it decreases. Pair production, it's the only interaction that the cross-section increases with photon energy. Of course, it exhibits also these thresholds. It's there. Another thing with respect to the atomic energy, Z, the pair production atomic cross-section is proportional to Z squared. It's like Rayleigh. Rayleigh, now we're talking atomic cross-sections. We're not yet at the level of mass cross-sections. Atomic cross-sections, remember, it's a cross-section per atom. For Rayleigh, it's proportional to Z to the power 2. For Compton, it is proportional to Z. For photo effect, it's proportional to Z to the power 4. And for pair production, it's proportional to Z squared, like Rayleigh. And the energy transfer for pair production, regardless if it's pair or if it's triplet, nuclear pair or triplet production, it is given by this relationship, and this is how it looks like. Okay. The last interaction is photonuclear disintegration. So I just have one slide for it. It's basically, we have a photon, it interacts with the nucleus. The nucleus will then take this energy of the photon, and then it can emit a neutron, can emit a proton, can undergo disintegration, can do other stuff. So this happens when a high energy photon is absorbed by the nucleus of the absorber. So we can have a neutron being emitted or proton being emitted. And usually when that happens, the nucleus becomes unstable, so it might undergo some radioactive decay process. So the absorber atom is transformed into a radioactive reaction product. Okay? This is why in a linear accelerator, we usually tell the therapist when you enter the room, try to be a little bit away from the LINAC head. Okay, if you take, for example, a servometer after we have a radiation of 15 or 18 MeV, you go inside and you put the servometer there, you will find that there is some radioactivity, going on. But this, luckily, it's very, very fast. It has a very short half-life, so it decays very, very quickly. So the threshold is of the order of 10 MeV or higher. Okay, again, it's like nuclear pair and electronic or triplet production. It has a threshold. Threshold is of the order of 10 MeV. If you notice in some of the regulations, like books for shielding and so on, they tell you, okay, Neutrons, you start to worry about neutrons shielding when you have an energy of 10 MeV or higher. This is why. It's because neutrons are produced from photonuclear disintegration interactions, whether it's from the head or from the patient. So the threshold is of order of 10 MeV or higher, with the exception of deuterium and beryllium, where the threshold energy is around 2 MeV. The bottom line is even this interaction is one of the interactions of photo interactions with matter, is probability or the cross sections of this interaction compared to the other interactions we discussed is much smaller. That's why when we're doing dosimetry on patients, usually we don't really take this into consideration. We ignore it because we know it happens, but it's irrelevant when it comes to dosimetry. It has a relevance when we're dealing with shielding, especially the neutron production and how to shield for neutrons. Okay. So the total cross sections, or before that, let's look at a summary. I tried to have one slide to summarize things for you. For photoelectric effect, the atomic cross section is proportional to the Z to the power 4. And it's inversely proportional to the energy to the power 3. And we said if we are in relativistic energies, this actually becomes inversely proportional to the 1 over the energy. Okay. The energy transfer is roughly given by this relationship where pK is the probability of photo effect happening or the vacancy happening in the K shell. Omega K is the fluorescence yield for a K shell. And H mu bar K is basically the mean energy of characteristic photons emitted from a vacancy in the K shell. Rayleigh scattering, the atomic cross section is proportional to the atomic number to the power 2, and it's inversely proportional to the energy to the power 2. And for Rayleigh scattering, no energy is transferred to electrons. So the energy transfer fraction is equal to 0 in this case. Compton scattering, the atomic cross section is proportional to Z, atomic number Z. And the atomic cross section decreases with energy. For the energy transfer, we use this graph, this sigmoidal graph. This will tell us the mean energy transfer for Compton scattering. And the last interaction is pair production. Pair production is proportional to Z to the power Z squared. And sorry, this should be increases with energy. It's not it increases with energy. And the energy transfer fraction is given by this simple relationship. So this is the summary of the 4 important interactions for us. Triplet production, yes, it's there, but its probability of cross section compared to a nuclear pair is negligible. That's why nuclear pair is a good representation of pair production. Thomson, that's a classical interaction. And what else? Photonuclear disintegration. Again, the cross sections are very, very low. So these are the 4 important interactions that usually medical physics will be with these 4 interactions. So what happens after interaction happens? After photon interactions, some of these interactions can produce a vacancy. And we know whenever we have a vacancy, the atom is going to undergo atomic relaxation, either emission of characteristic X-rays or emission of Auger electrons, or both, right? It needs to relax. So which photon interactions will create vacancies? Photo effect will create a vacancy. Compton scattering will create a vacancy. And triplet production will create a vacancy. So these three interactions, they will create a vacancy in the atom. And we know that the vacancies will be filled by orbital electrons making transitions, and this will result eventually in the emission of characteristic X-rays or Auger electrons. Okay, and this proportionality, or which one is going to happen, is governed by the fluorescence rate. Another thing that is possible after photon interaction is a production of positrons. So this happens in pair and in triplet production. So when we have a positron produced, eventually the positron is going to annihilate with an orbital electron. So the positron initially has some energy. It's going to move, ionize, do whatever it wants. But when it loses its energy, it's going to find an orbital electron and is going to annihilate with the orbital electron. And when this happens, then we will get two annihilation photons produced with energies of 0.511 each, that energy, and they are approximately at 100 degrees, 180 degrees from one another. They're not exactly at 180 degrees, but will be emitted at approximately 180 degrees to each other. Okay, it is possible. Of course, when we have this annihilation happening, okay, we get a vacancy, right? And then it's followed by also emission of characteristic X-rays and Auger electrons. I don't know if I mentioned this when we talked about characteristic X-rays and vacancies. There are 8 processes that I know of that can actually result in vacancies. So 3 of these are actually with photon interactions, photo effect, Compton, and triplet. And then here, this is the 4th way of producing a vacancy, annihilation of positron. So we don't care from when the positron is generated. It could be from beta plus emission, nuclear decay, or it could be actually after following, pair production, we get the positron. We don't care from where the positron originated, but after positron is produced, this is going to happen. Sometimes the positron might actually annihilate before it loses all of its energy. It's possible. And in this case, we call this annihilation in flight. And when annihilation in flight happens, we can get a single photon, 2 photons, 3 photons. It's not necessarily we get 2 photons, although the probability is very, very low for this to happen. Most of the time, the positron is going to lose all of its energy and then annihilate with an orbital electron. But it's possible that it can undergo annihilation while it did not lose all of its energy. And this is what we call annihilation in flight. So the mass attenuation coefficient, total atomic cross-section, is basically we sum the cross-sections of all interactions. In this case, I've limited them to the 4 dominant or the 4 important interactions: photo effect, Compton, Rayleigh, and pair production. The others, they're negligible compared to these 4 interactions. So this is the total cross-section. It's just the sum of these atomic cross-sections. This is a plot of these photon interactions. This is photo effect. And here we have, this is Compton interaction. Here we have these curves here, they represent Rayleigh. And here on the right, bottom right, this is for pair production. So these are the atomic cross-sections. So the atomic cross-section is basically a cross-section for a single atom. So the question will arise is, if I have a gram of these atoms, what is the cross-section? So all what we need to do, we look at 1 gram of a certain substance, and we count how many atoms do we have in that, in 1 gram. And this is what we call the mass attenuation coefficient. So the mass attenuation coefficient is basically these atomic cross sections, but now we add them for all atoms in 1 gram of that substance. So the mass cross section is the sum of the atomic cross sections in 1 gram of medium. For lead, get me 1 gram of lead, and all what I'm going to do is just take the cross section of 1 atom of lead and multiply it by the number of atoms in 1 gram. That gives me the mass attenuation coefficient. So the number of atoms in 1 gram of medium is given by N of Avogadro by the atomic mass. So to get the mass cross-section from the atomic cross-section, all what we do, we multiply the atomic cross-section by, we multiply the atomic cross-section by Na over 8. That will give me the mass attenuation coefficient. And the SI unit, or the unit that usually represent mass attenuation coefficients, is in centimeters squared per gram. For the atomic cross-section, it's bars, so it's centimeter squared per atom. Here it is centimeter squared per gram. In the first lecture, we said, okay, the atomic mass for elements is approximately equal to 2Z. So in general, we will have number of neutrons roughly equals to the number of protons. The exception is when we have high Z material. Then we see that we have more neutrons than protons. And we said that this ratio of Z over A is 0.5, but slowly decreases as we increase Z. I think for high Z materials, it goes down to 0.35. The only exception is hydrogen. Z over A equals to 1. So this thing, A for hydrogen is 1, and we have 1 proton there. So this rule does not apply for hydrogen. And helium-3 also. Helium-3 has 2 protons and 1 neutron. So again, Z over A is about 0.66. So these are the 2 elements that are exceptional. But any other element, Z over A approximately equals to 0.5, and then but slowly decreases as Z increases. So why I'm bringing this up? Because now we in the past, in the summaries, this year, we've talked about the dependence of each interaction with respect to Z for the atomic cross-section. Now, if we want to look at the mass attenuation coefficient and the dependence on Z, the dependence of Z is decreased by 1. So for example, for photo effect, the dependence on Z for the atomic cross-section is Z to the power 4. For the mass attenuation coefficient, the dependence, sorry, this is Z to the power 3. I have to fix this. Okay. So this is 1 less Z to the power 3. This is the notation. We put the cross-section divided by density. This is the notation of the mass attenuation coefficient. Okay, this is how we, sometimes they would put, for example, mu sub m. That's also another notation for the mass attenuation coefficient. So for Compton, for example, Compton, the atomic cross-section depends on Z. So the mass attenuation coefficient does not depend on Z for Compton. Z to the power 0 has no dependence on Z. So the mass attenuation coefficient for lead and copper are roughly equal the same. Okay. The only exception is hydrogen. Hydrogen actually has a higher mass attenuation than lead for Compton. Why? Because we have Z over A equals to 1. Whereas for lead, it's 0.35. So for hydrogen, the mass attenuation coefficient actually is the highest for all elements. That's the mass attenuation coefficient. Don't confuse this with linear attenuation coefficients. Remember, the mass attenuation coefficient is the attenuation per gram. Get me 1 gram of hydrogen and get me 1 gram of lead. The mass attenuation coefficient in 1 gram of hydrogen is actually higher than 1 gram of lead. Okay, for Compton, I'm talking about Compton scattering. So this is what happens to the mass attenuation coefficient. The dependence on Z is actually lesser by 1. Rayleigh, for example, we said the atomic cross-section depends on Z squared. So the mass attenuation coefficient for Rayleigh depends on Z, 1 less. This is the last slide I have for today. This is a summary of these interactions. Okay, talks about what is the interaction, the 4 important interactions: photo effect, Rayleigh, Compton, and pair. Mode of photon interaction. So what happens to the photon? Whenever we want to define an interaction, we need to say, okay, what happens to the photon? It could disappear, it could be scattered with the same energy, could be scattered with the lower energy, and so on. The energy dependence, okay, for each of these 4 interactions. And the threshold. So we said there is a threshold for pair production, roughly about 2 MEC squared. Now here for Compton and for photo effect, the threshold is actually the binding energy of the electrons. Okay, if the energy of if we can transfer to the electron energy higher than its binding energy, yes, then this interaction can happen. This is the linear attenuation coefficient. We'll talk about this next time, inshallah. And the atomic coefficient depends on Z. So this is the atomic cross sections. Z to the power 4, Z squared, Z, and here Z squared for pair production. And here we have the mass coefficient dependence on Z. So here you see 4, it became 3. Rayleigh, 2 became 1. Compton, Z, independent of Z. And then finally, for pair production, Z squared becomes the mass attenuation coefficient for pair production becomes dependent on Z. So I think this is the last slide for today. Don't know if you have any questions. It's,